systems of linear equations. And we took a little bit of a digression, and we said that systems of linear equations, which we represent as AX is equal to B, we can also think about them in another way. We can think about that matrix A as representing some sort of linear transformation, and so AX is equal to B is really just saying that you've got a vector X which is being transformed by this matrix A into another vector B. So we're going to keep talking about systems of linear equations today, and our goal today is the following. We're going to show that every system of linear equation, there are only three different types of behavior that we can get out of this. Either it's got no solutions, it's got exactly one solution, or it's got an infinite number of solutions. You can't have a system of linear equations which has, say, 4 solutions. That's not going to happen. It's going to be 0, 1, or an infinite number of them. And then when we come back on Monday, we'll start speaking about subspaces. Okay. So to start today, we just need to introduce a piece of terminology. And we're going to distinguish between two different types, two different types of systems of linear equations. We're going to distinguish between what are called homogeneous and inhomogeneous, or non-homogeneous systems. So let's write some of this down. So the system of linear equations AX is equal to 0, right? So a system of that form, AX is equal to 0, where the right-hand side isn't an arbitrary vector B, it's actually the 0 vector, is called a homogeneous. Is called homogeneous system of linear equations AX equal to B with B not equal to the 0 vector. Right, so AX is equal to 0, homogeneous, AX is equal to B, B not equal to the 0 vector, is called inhomogeneous or non-homogeneous. So if that's our goal up there, we want to show something about every single system of linear equations. What we're first going to do is we're going to try to show something about the homogeneous case. And once we've shown something about the homogeneous case, I'm speaking about the non-homogeneous case. So let's speak about the homogeneous case first. So the homogeneous case. And we'll start with fact 1.4. I realized that I said something yesterday which I called a fact in my notes, but I didn't call it a fact yesterday. What I said yesterday was that every linear transformation from Rn to Rm can be represented by a matrix, and every matrix is associated to a linear transformation. I called that a fact in the notes. I didn't call it a fact in the handwritten notes yesterday. So we're on to fact 1.4 now, even though the last fact I wrote down was fact 1.2. I just want to keep the numbering here as consistent as possible with the typed up notes. Okay, so fact 1.4 is the following. Every homogeneous, or any homogeneous, a homogeneous system if you've got a homogeneous system of linear equations, it's consistent. It's always going to have at least one solution. There's no way to write down a homogeneous system of equations which doesn't have a solution. And if we just scroll up and we take a look at, in fact, no, it's not really necessary to scroll very far. That's our homogeneous system over there. AX is equal to 0. Can anyone tell me what is this one solution that every homogeneous system should have?
0.
Yeah, you just, okay, not A is equal to 0, X is equal to 0, right? So this matrix A is fixed, but however you fix the matrix A, you can always just choose X equal to 0, right? It's not a very interesting solution. It's in fact sometimes called the trivial solution. So let's write that down as well. Here's, in fact, hold on, I think I was putting facts in a different color. Or if I wasn't, I should have been. Right, so fact 1 point. And let's see, what's our explanation here? In fact, I think it was the other way around. Well, whatever. Doesn't matter so much. Can anyone remember what colors I was using yesterday for the facts? Was it blue and black? Okay, all right, fine. So we will keep that fact blue, and we'll keep this explanation in red. Right. So this is called the trivial solution. Every homogeneous system has the trivial solution. You can always find at least one solution. It's not very interesting, but here it is. There's some other really nice results or some really nice behavior for homogeneous systems of linear equation. Let's put this up as fact 1.5. Which is that if you take any linear combination of solutions to a homogeneous system, that linear combination is still a solution. Right, so any linear combination of solutions to a homogeneous system of linear equations is still a solution. And we can write up an explanation for that as well. Okay, so let's just say we've got two solutions, call them x and y. In fact, not x and y, let's call them u and v. Consider two solutions, u and v, to ax is equal to 0, right? That's just saying that a multiplied by u is equal to 0 and a multiplied by v is equal to 0. That's what it means for a vector to be a solution. You take matrix A and you multiply it by that vector, you get 0. We want to know about what happens when you apply the matrix A to the linear combination alpha u plus beta v. What happens when we apply this? What happens when we apply this matrix A to this linear combination alpha u plus beta v? So look at that for a bit and think about it. What do you know about this matrix A? Someone mumble that louder. It's linear, right? What does it mean for a matrix to be linear? What does it mean for a transformation to be linear? Okay, sure. So there's something about pulling these constants outside. We said yesterday that this linear transformation sort of respects vector addition and it respects scalar multiplication, right? So we can, let's split it up in terms of the addition first. This is the same thing as A acting on alpha U plus A acting on beta V. Now there may be two lines you want to write underneath this. Go ahead and see if you can write them down, but convince yourself that over here is equal to that, is equal to this, is equal to this, is equal to 0, is what we're eventually hoping to write here. Let's see, how many lines will we need? Let's say we'll need 1 line, 2 lines, and probably over here we can do that. So take a minute and see if you can fill in what should go in those 2 lines in that little gap. Okay, so what do I write down next? And then? Yeah, this is alpha times by 0 plus beta times by 0 because alpha u is a solution. Oh, sorry, alpha u is 0 because u is a solution. Alpha v is 0 because v is a solution. So what we've used over here in this first little bit, come that far, we've used linearity. And then this little step here, we've used U and V are solutions, right? So a linear combination is also a solution. Okay, great. So we can take a linear combination of solutions to a homogeneous system of linear equations, and it's still a solution. The next fact, fact 1.6. Let's put them in the right order. Okay, yeah. So we know that our system of linear equations, if it's homogeneous, it definitely has at least one solution. It's got this solution, which is just a trivial solution. Your vector x is just a 0 vector. So this is saying if you can find one other solution, one solution which isn't just the 0 vector, then you should be able to find an infinite number of solutions. So as far as you're concerned with the homogeneous case, this is saying you either have one solution or you've got an infinite number of solutions. So if we can find a non-trivial solution, how do we find the rest of them? How do we find an infinite number? Yeah, sure, you just take a linear combination of that one with itself, which is really just saying you take all the scalar multiples of that non-trivial solution. All the scalar multiples of that non-trivial solution are still non-trivial solutions. Right, so if we write down an explanation, in fact, maybe you can take 2 minutes, write down an explanation for yourselves, and then I'll put something up. But do try to write something down, right? The idea is just that if you've got a non-trivial solution and you multiply it by a scalar, it's again a non-trivial solution. So as soon as you've got one, you've got an infinite number. Okay, so you might write down something like this. If U is a non-trivial solution, maybe we'll write down what it means to be non-trivially a non-trivial solution, so i.e. u is not equal to the 0 vector, then alpha u, right, so every scalar multiple is also a solution, also a non-trivial solution for alpha element of, okay, let's just be careful the way I've written it down here, for any scalar except 0, right? For any scalar except 0, alpha u will be a non-trivial solution. When I'm teaching this course, a lot of people in past years have said to me, do I need to remember all these facts? Right. And that's the wrong way to think about this. When you're in junior school, even before junior school, when you're in pre-primary, or even before you go to pre-primary, when you're, like, I don't know, at home, you're very small with your parents, and you start learning about mathematics, and you start adding things together, and you say, well, 2 plus 3 is 5, and 3 plus 6 is 9, and 9 plus 2 is 11. God, there are an infinite number of facts that you need to remember about adding two things together, right? If you try to remember all the possible results of all the possible additions, it's impossible. Addition looks like an impossible thing to do. But if you understand what addition is, you immediately get everything, right? So these facts are all really simple consequences of the fact that the matrix represents a linear transformation. And as soon as you get your head around linearity and what it means for a transformation to be linear, all of this immediately just sort of tumbles out for free. So don't try to think of this as, this is a fact I must remember, this is a fact I must remember, this is a fact I must remember. They're all facts that are all true for the same underlying reason, and the same underlying reason is just that the matrix represents a linear transformation. Okay, so that's something to sort of bear in mind as we go through this course. It might look like there's a lot of material, but very often it can all just be distilled down to a single observation, and it's all just variations on a theme. All right, so the next thing we want to say is, I actually want to go ahead and start defining a couple of other things and give names to these solutions, right? And there are two sorts of names that you will sometimes see. You'll see either kernel or null space. So if we've got a homogeneous system, AX is equal to 0, we can create a set, which is just a set of all the solutions. And that set of all the solutions to that homogeneous system gets a special name. It's called the null space or the kernel. So let's write some of this down. The set of all the solutions to a particular homogeneous system of linear equations, set of all the solutions to a particular homogeneous system of linear equations. It's called the null space or kernel. For the most part in this course, I think we're going to use the terminology null space rather than kernel. But if you're reading books in the library or looking at things online, you might see a kernel. And you should just understand it means the same thing. And we can define it in the following way. Or maybe we've already defined it like that. We can write it down in the following way. We'd say, the null space, which is normally denoted NS, null space, of a matrix A, or the kernel of a matrix A, is the following set. It's a set of all the vectors x, so that A multiplied by x gives you the 0 vector, right? And the null space is very clearly not an empty set. There's at least one thing in the null space, and that thing in the null space is just the 0 vector, because we said that the 0 vector solves every homogeneous system of linear equations, right? So the null space has at least null. Okay, the null space is always going to have, at the very least, that 0 vector in it. And we can maybe just think about the null space of a particular matrix or of a particular linear transformation. So let me put this here in pinkish purple. We'll look at an example. We're going to think about a projection matrix. We're going to think about, let's say, we're going to think about the linear transformation, which is a projection, and the matrix which represents that projection. And we'll think about its null space, right? So consider the projection of, and let's just work in R2. Consider the projection of R2 onto the x-axis. This has a matrix representation. And you should have seen last year that projections are a linear transformation, along with things like rotations and reflections and so on. This has a matrix representation. P is equal to, and it'll be a 2 by 2 matrix because we're taking R2 back into R2. So what are the entries of P? Does anyone remember? Maybe we can sort of puzzle it out. What should the entries of P be? Okay, so 1, 0, that's the suggestion for the first column, and the next column? 0, 0, right. Okay, so what this does is, if you were to multiply this, you've got a vector here, x, y, you'll get 0, x, y, so that gives you 1x. So your x component stays x, and then you get 0, 0 multiplied by x, y, so your y component just becomes 0. So it takes some vector x, y, and all it does is it makes the y component 0. All right. So if we think about what this does graphically, or geometrically, we have the following picture, right? You've got R2 over here, you've got a y-axis. Okay, you've got some point here. That point will be projected in the following way. This point here gets projected in the following way. This point over here doesn't move at all. It just stays where it is. This point way up here all comes straight down. That's the action of P, and so on. Right. So the question is, what is the null space of this transformation? So think about that for a minute. If you want to write it down, you can write it down. If you just want to describe it in words, you can do that as well. I mean, think about it. Okay, so what is the null space of P? Any takers? The y-axis, right? The null space of P is just the y-axis, because everything on the y-axis is projected onto the 0 vector. And the null space of P is supposed to be all the vectors that, when you transform in them, in this case when you project them, you get the 0 vector, right? The null space of P, what is the null space of P? You could write down this. Null space of P is the y-axis. That's perfectly fine. Maybe you prefer to write it down symbolically. You'd say something like this. It's the set, what is this? We want the y-axis, so it must be something like 0 alpha. Alpha is an element of the reals, right? But the important thing to realize is that your null space, this over here, that's your null space of P. Everything in the null space gets projected down onto the origin. Yes? Why is it the y-axis, not the x-axis? Well, let's say we take a point somewhere on the x-axis over here. That point over there. And we project that point onto the x-axis. It stays exactly where it is, right? So that says, for example, that A multiplied by, I don't know, maybe that's A acting on the point 1, 0 is the point 1, 0, right? But the null space is defined as, it's got to be all the vectors that when A acts on them, it gives you 0, right? So there's no way 1, 0, there's no way something on the x-axis can be there, because it stays on the x-axis away from the origin. On the other hand, if we act on a point over there, if we acted on that point, right, that gets projected down onto the origin, so that would be in the null space. So it's not the things that are left unchanged, it's the things that get transformed or sent to the origin.
So is the null space like the point to like
your null space, okay, we'll talk about this in a little bit more detail when we come back on Monday. Your null space will be a subspace of the entire vector space. So in this case, our whole vector space is all of R2, and the null space is just some part of it, which in this case is that straight line, the y-axis. But in general, it'll be a subspace, and we'll talk a little bit more about what subspaces are when we come back on Monday. All right. Are there any questions about what we've done up to this part? Because now we're going to start speaking about the inhomogeneous case, or the non-homogeneous. All right. So we spoke about all of this over here, right? All of this. We're speaking about the homogeneous case. So if you've got AX is equal to 0. So now we're going to talk about the non-homogeneous case. We're going to talk about the non-homogeneous case. Fact, and we are now up to fact 1.7. Fact 1.7 is the following. So if U solves let's say solves a non-homo system of linear equations. So if you've got a vector U which solves the non-homogeneous system of linear equations, and let's see, and W solves the, and I'm going to write down here the associated homogeneous system of linear equations. I haven't defined that yet, but it's sort of very obvious what it is. We'll talk about that in a moment. And then U plus W. Okay. So we've got a vector U which solves a non-homogeneous system of linear equations. We've got another vector W. W solves the associated homogeneous system of linear equations. So what I mean by that is that if our original vector U solves AX is equal to B, then this vector W solves AX is equal to 0. And the claim is that if you add these two things together, if you add U and W, it's still a solution to that equation AX is equal to B. And we can write this down, write out an explanation, and again the explanation relies entirely on the linearity of A, of this matrix, of this transformation. So we write this down here, explanation. So we have U so that AU is equal to B, and W so that AW is equal to 0. What I'd like us to show is what happens when we apply A to U plus W. And you've got a minute to think about this, just write down do what comes naturally, right? There's not a lot we can do here. All we have is linearity of A and these two conditions on U and W. such that, or so that. Okay, so what do I do next? What do I write down over here? Yeah. AU plus AW. And what is AU? B. And what is AW? 0. And what is B plus 0? Yeah, they're very good. Right? So there we go. We've explained this. And again, it's all very obvious once you understand that linearity is what's important here. Okay? And here's a sort of related, but not exactly the same. You'll have to think about how this differs. Fact 1.8 is the following. It says that if I've got two solutions, U and V, and they both solve the same non-homogeneous system of linear equations, then the difference between these two solutions solves the associated homogeneous system. Okay, so let's write that down. So if U and V are any two solutions to a non-homogeneous system of linear equations, U and V are any two solutions to a non-homogeneous system of linear equations, then W, which is their difference, solves the the difference solves the associated homogeneous system. And again, you've got, a minute. You can write down an explanation for this very quickly, again, just using the linearity. So we write down something like this. It's very quick. A acting on W is the same thing as A acting on U minus V. That's the same thing as AU minus AV, which is the same thing as B minus B, which is 0. Right? And all we've done is we've used the linearity of A and the fact that U and V are solutions to the non-homogeneous system of linear equations. Okay. So between fact 1.7 and 1.8, can we squeeze them both on? Yeah, just about. Between fact 1.7 and 1.8, we can now say the following. If I have one solution to my non-homogeneous system, so I've got this non-homogeneous system, AX is equal to B, and I can find one solution to it. What I can then do is I can go to the associated homogeneous system, AX is equal to 0, I take any solution to that and I add it to my original solution, and that's still a solution to the non-homogeneous system. And further, every solution to the non-homogeneous system can be found in this way. So every solution to your non-homogeneous system can be found by finding just a single solution and then adding on something from the homogeneous solution space, something from the null space of A. So we can write that down as well. So between fact 1.7 and 1.8, we can now conclude the following. The facts 1.7 and 1.8 mean that every solution to a non-homogeneous system of linear equations, AX is equal to B, this again. Let me just write it down first. So that's quite wordy. Let me read it out and then I'll talk through it again. So fact 1.7 and 1.8 together, they mean that every solution to a non-homogeneous system of linear equations, AX is equal to B, can be written as X, whatever it is, can be split into two pieces. So there's XP, which is just a solution that we find as a particular solution to AX is equal to B, plus XH. And XH is something from the null space of A, so it solves the homogeneous system of linear equations. And further, everything that you write down in that form, X is equal to XP plus XH, is a solution. You're not accidentally going to write down something that isn't a solution by taking a particular solution and adding this solution to the homogeneous or the null space of A, right? Yes? No, it can have 0, 1, or infinitely many, which we're about to do in a moment, because a homogeneous, this null space of A, has either got one thing in it, which is just the 0 vector, or it's got an infinite number of things in it. So the solution to the non-homogeneous case, there are three options. Either we can't find a solution, or we can find one solution. It's either one solution plus just the 0 vector, or it's one solution plus an infinite number of things. So in a moment, that's what we're going to do. We're going to prove what we set out to at the start, where we said it's either going to be 0, 1, or infinite number of solutions using this sort of construction.
Why do we say that AB minus AB equals
No, B is the same. The U and V, let's just go back here. U and V, there are two solutions to, I said a non-homogeneous system of linear equations. I mean, they solve the same non-homogeneous system of linear equations. Okay, so they both solve the same AX is equal to B. That B is the same for both of those.
And let's say yes, it comes from different vectors of B and U.
Yeah. So this is just saying, if you write down something like AX is equal to B, there might be more than one vector which is transformed into B. So if we write down, let's just go back up here and take a look at this picture I wrote down. If I wrote down something like this, if I wrote down Px is equal to 1, 0, there are an infinite number of vectors that will satisfy that, right? Because this vector will be projected onto 1, 0, and this vector projects onto 1, 0, and this vector, and this vector. So there are a whole bunch of vectors that might all be projected onto the same place, all work with the same matrix P or A, the same output B, but then there may be many different solutions for that X. Okay. questions. I feel like there was one more hand. Yes?
That would be an example of
null space that has
Yeah, this one here. Yes, yes. I mean, because the y-axis is infinite.
what about
A single solution. Here, I guess maybe the easiest thing is just a reflection, right? Or even simpler than that, you have an identity matrix. The null space of the identity matrix, it takes everything and it leaves everything exactly where it is. The only thing which goes to the origin is the origin. Okay, so I mean, we'll talk about this some more. It turns out that linear transformations where the null space is exactly one element are really nice because those are invertible linear transformations. We'll come back to this later in the course. Yeah, generally A and B are specified in the problem, and we're trying to find X. All right. So let me just say that pretty much this conclusion that I've written up here, we're going to see again later on in the course, pretty much written out word for word, except instead of saying homogeneous system of linear equations, we're going to write down non-homogeneous differential equation. So everything we have learned now about systems of linear algebraic equations is going to have an analog when we get to linear differential equations. So this is not completely disconnected from what we're going to see. All right, okay, so we've had a lot of questions, and now we have to rush through this last little fact. Sorry. Fact 1.9. Inhomogeneous system of linear equations has either no solutions, exactly one solution, or infinitely many solutions. And I already sort of talked through the explanation earlier in response to a question, but let's write this down again. And I maybe don't have time to write it down in very neatly or in full. So what I'm going to do is I'm just going to give you the basic outline. And if you want to, you can sort of flesh it out yourself. Maybe take a look at the notes and see how it's done in the notes. But the basic outline is this. And really, this is just the outline of main ideas. What we say is we've got this system of linear equations. Either it is inconsistent or it's consistent, right? So you think about it like this. You say either it's inconsistent, system of linear equations is inconsistent or it's consistent. If it's inconsistent, then 1 is true. If it's consistent, then we do the following. Null space of A is, and your null space of A can either be just a single element, which is the 0 vector, or the null space of A could be infinite. And if the null space of A is just a single vector, the 0 vector, then 2 is true. Otherwise, 3 is true. So that's the sort of basic skeleton of how you would go about proving or explaining why this must be the case. So take a look at this, see if you can flesh it out yourself. If you can't flesh it out yourself, take a look at the notes, and it should be fleshed out in those printed notes. Again, I'll hang around, so if you've got any questions, you can speak to me. And also, please, if you haven't signed up for a tutorial slot, do that today, because I'm going to sit down with the registers today, and I want to work out who has or hasn't attended TUTS and what we're going to do next week. So please, if you haven't signed up, do that today.